Okay, let's start the following part. Analysis of normalization techniques. In the first part, we provided a high-level motivation of normalization in benefit network optimization. In this section, we will further discuss and analyze other properties of normalization methods in improved deep neural networks training performance. Regarding to the theoretical analysis of machine learning or deep learning, it usually involves three main topics, that is the representation, optimization, and generalization. The model representation mainly covers to quantitatively measure the complexity of the deep models, and theoretically characterize how does the depth of deep neural networks benefit the representation capacity compared to the width, and so on. Optimization mainly research on given a model and the optimization algorithm, whether a stationary point can be obtained or how fast the optimization algorithm to arrive the stationary point. Another major part of potential theoretical foundations are the generalization ability, which refer to the capacity of models when trained on the training data by deep learning algorithms, predicting on the unseen data. In this tutorial, we mainly focus on batch normalization because it displays nearly all the benefits of normalization in improve the performances of deep neural networks. For example, stabilizing training, accelerating convergence, and improve the generalization. We will show how batch normalization benefits optimization and generalization, and show how BN affects the representation by using its batch size to control the distribution. We just said there remains little consensus on the exact reason and the mechanism behind BN's performance. The theoretical analysis for BN and its effectiveness in deep neural networks is still an active research topic. Here, we do not discuss the rigorous theoretical analysis, for example, what is the bound of excess risk or generalization errors of normalized models, or whether BN can improve the theoretical convergence rate. It is difficult for the theoretical deep neural networks, even though there is no normalization in the network. What this tutorial is mainly focused on illustrating the analysis that combines high-level theoretical intuition and the empirical experimental validation. One essential functionality of batch normalization is its ability to stabilize training. This is mainly due to its scale-invariant property. That is, it does not change the prediction when rescaling parameters and works by adaptively adjusting the learning rate in a layer-wise manner. Specifically, in this widely linear normalization and nonlinear analysis of a network, we can say if we multiply the weight W with the scale A, the output does not change. This means the prediction of a network is not sensitive to the scale of its weight if batch normalization is used. One interesting phenomenon is that this scale affects the gradients of network. It is inversely related to the scale A. This mechanism has a good property for adaptively adjust the learning rate. The scale-invariant property also applies to other methods that normalize the activations or weights, for example, layer normalization or weight normalization. This property was first shown in the original BN paper and then investigated in the layer normalization paper to compare different normalization methods. Huang et al. Extends this analysis for rectifier networks and shows how and stabilize training in the network by investigating scale dynamics for network. From the perspective of a practitioner, two phenomena related to the instability in training a deep neural network. First, the training loss first increases significantly and then diverges. Or second, the training loss hardly changes compared to the initial condition. The former is mainly caused by weights with large updates, for example, exploded gradients or optimization with a large learning rate. The latter is caused by weights with few updates, that is, due to vanished gradient or optimization with a small learning rate. Given a rectifier neural network with positive homogeneity nonlinearity, if the weight in each layer is scaled by a factor of alpha k, we have the corresponding layer input and output gradient, weight gradient shown here. For unnormalized network, we observe that the scaled factor alpha k of the weight in layer k will affect all other layers' weight gradients. Especially, if all alpha k larger than 1, the weight gradient will increase exponentially for one iteration. Moreover, such an exponential increase in the weight gradient will be sustained and amplified in the subsequent iteration due to the increased magnitude of the weight caused by updating. That is why the unnormalized neural network will diverge once the training loss increases over a few continuous iterations. For normalized network, the scaled factor alpha k of the weight will not affect other layers' activations or gradients. The magnitude of the weight gradient is inversely proportional to the scaled factor. Such a mechanism will stabilize the weight growth or reduction. The scale invariant of the weight has an altering effect of the learning rate. If a network is scale invariant, for example, if lambda w equals f of w, we can derive that the weight vector is perpendicular to its gradient. Based on the weight update rule shown in this formulation, we can obtain that the norm of wt plus 1 equals the norm of wt plus this positive term. Thus, this property can lead the norm of the weight to increase after each iteration. The increased weight will inversely affect the scale of the gradient, which leads to the decrease of the gradients. This can be viewed as an equivalently decrease of the learning rate. Another research direction is to analyze the effect of weight decay when combined with scale-invariant normalization. In this case, weight decay causes the parameters to have small norm, and the scale-invariant update drives the weight to have large norm. Therefore, it can be obtained in equilibrium states for weights. Okay, as stated in previous sections, one motivation behind batch normalization is that widening the input can improve the conditioning of the optimization and thus accelerate training. This motivation is theoretically supported for linear models, but it is difficult to fuse the extended to deep neural networks. Therefore, there exists work to calculate the spectrum of the hashing matrix empirically to support these claims by experiments. Jobani et al. Empirically investigated the conditioning of the optimization problem by computing the spectrum of the hashing for a large-scale dataset. From this table, we can see that the batch normalized network has more centralized eigenspectrum, and the maximum eigenvalue is significantly smaller than the unnormalized network. This shows the best normalized model has flatter optimization landscape. One motivation behind PN is that widening the input can improve the condition of the optimization. This motivation only holds under the condition that PN is placed before the linear layer, while in practice, PN is typically placed after the linear layer. As discussed in the introduction and motivation of the first part, it shows that one way to improve the conditioning of the optimization problem is to satisfy criteria 2, that is, the covariance matrix of the input and the output gradient are well conditioned. Huang et al. Experimentally observed that Bn not only improved the conditioning of the near input the covariance matrix, but also improved the conditioning of the output gradient covariance. As shown in these figures, it has been shown that central data is more likely to be well conditioned. This suggests that place Bn after the linear layer can improve the conditioning of the output gradient, because centering the activation with the gradient backpropagating through such a transformation also centers the gradient. Other analyses of normalization in optimization include an investigation into the signal propagation and the gradient backpropagation. Based on the mean field theory, besides, the work of Corral et al. Demonstrated Bn obtains an accelerated convergence on the possibly non-convex problem of learning half spaces with Gaussian inputs. From a length-direction decoupling perspective, Dokkan et al. Further provided the first global convergence result for two neural networks with random activation trained with weight normalization. One important property of batch normalization is its ability to improve the generalization of deep neural networks. It is believed such an improvement is obtained from the stochasticity or noise introduced by normalization of batch data. It is clear that both the normalized output and the population statistics can be viewed as stochastic variables because they depend on the mini-batch inputs xm, which are sampled of datasets. Therefore, the stochasticity firstly comes from the normalized output during training. Besides, it also comes from the discrepancy of normalization between training and inference. That is, during training, one uses the mini-batch statistics, while during inference, one uses the estimated population statistics. Okay, Huang and Szejedy was first to show the advantages of this stochasticity for the generalization of networks. Like dropout, it provides a good equation of the stochasticity of batch normalization. Huang et al. Proposed an empirical evaluation for the stochasticity of normalization of batch data, called the stochastic normalization disturbance. The empirical estimation of HND for sample X of the normalization G is defined as follows, where X denotes the number of mini-batches that are randomly sampled from the dataset. HND can be used to evaluate the stochasticity of a sample after the normalization operation. Here is the illustration of HND with different batch sizes. We sampled 3,000 examples, black points from Gaussian distribution, and show a given example X, for example here, red cross, and its being outputs here the blue plus sign. When normalized over different sample size xb, the left figure and the right figure shows the results with batch size b of 16 and 64 respectively. We can find that small batch size has more noise distribution and larger SND, when large batch size has more compact distribution and small SND. It is also interesting to investigate the stochasticity of different normalization operations. Here, we show how the normalized output of one sample changes when combined with a different sample set xb by performing batch normalization, PCA whitening, ZCA whitening, and CD whitening. It is clear that the distribution of the PCA whitening output of one sample is very sparse, which means that had X has significant diversity. This suggests that PCA whitening provides large stochasticity. On the other side, the Bayesian standardized output shows a tight Gaussian-style distribution, which suggests that Bayesian has smaller stochasticity. Note that Bayesian cannot guarantee that the normalized output has an identity covariance matrix, while other whitening methods can. Similarly, it can be found that ZC whitening provides reduced stochasticity compared to CD whitening. In fact, ZC whitening has been shown to minimize the total squared distance between the original and whitened variables. For batch normalized networks, the stochasticity is related to the batch size m and the dimension d. Here, the left figure shows the SND of different normalization methods with respect to the dimensions. When fixing the batch size, we find that PCA whitening shows the largest SND while being the smallest of all the dimensions, which is consistent with the illustrative observation shown in the previous slides. We notice that all normalization methods have an increased SND when the dimension increases. Besides it, this has a smaller SND than CD of all the dimensions. The right figure shows the SND of different normalization methods with respect to the batch size when fixed the dimension. An interesting observation is that PCA whitening has nearly the same large SND among different batch sizes. This suggests that the PCA whitening is extremely unstable, no matter how accurate the estimation of the mini-batch covariance matrix is. This effect is in accordance with the explanation of stochastic axis swapping, where a small change of the examples when performing PCA whitening results in a large change of representation. In the previous slides, we show one can use the group-based method to control the magnitude of batch whitening. Here, we show that this group-based whitening methods can be well used to control the stochasticity and to trade off the improved conditioning and introduce the stochasticity of whitening. The left figure shows the SND of different whitening transformations by varying their group size ranging from 2 to 512. The right figure displays the spectrum of the covariance matrix of the whitened output based on groups. It can be found that the group size effectively controls the SND of the ZCA or CD whitening. With decreasing group size, ZCA and CD whitening show reduced stochasticity, as shown in the left figure, while having also degenerated conditioning as shown in the right figure. since the output is only partially whitened. Besides, PC whitening still has a large SND of all group sizes, and with no significant differences. This observation further corroborates the explanation of stochastic X-swapping, that is, the PC whitening is extremely unstable. The left figure also shows the SND of the approximate ZC whitening method, here called ITN, which uses Newton's iteration to approximate and calculate the whitening matrix. ITN 5 is indicated as the ITN method with an iteration number of 5. An interesting observation is that ITN has a smaller SND than BN. When using a large group size, for example 256, with a smaller iteration, for example t equals 5, this suggests that we can further combine group size and iteration number to control the stochasticity of ITN, providing an efficient and stable solution to approximate this whitening. There are also work tried to model the stochasticity theoretically. For example, Alexander et al. Jointly formulated the stochasticity of the normalized output and the discrepancy of normalization between training and inference in a mathematical way, under the assumption that the distribution of activations of the full dataset is approximately Gaussian and IID. Here, considering an example X, its mini-batch output can be formulated as this. Under the assumption, this term is a normal distribution, and this term is a Kappa distribution. Therefore, the output is theoretically modeled. In this part, we will show different normalization indeed has the effects on the representation of the neural network, and the effects can also relate to their hyperparameters, for example, the group number of group normalization and the batch size of batch normalization. Huang et al. Experimentally showed that group whitening or group normalization has a significantly degenerated training performance when the group number is large, which is similar to the small batch size problem of batch whitening or batch normalization. They attribute this to the constraints on the output imposed by the normalization operation, which affect the model's representational capacity. For illustration, this figure shows the histogram of normalized output by varying the channel number in each group of group normalization and the batch size of batch normalization. It can be found that, first, the values of normalized output are heavily constrained if C or M is too small. For example, the value of normalized output is constrained to be -1 and 1 if C equals 2. Second, the normalized output is not Gaussian if C or M is too small, while batch normalization or group normalization aims to produce a normalized output with a Gaussian distribution. Eventually, these constraints can be represented as a system of equations of the normalized output. For example, the BN's constraints here. Huang et al. Also defines the constraint number of normalization to quantitatively measure the magnitude of the constraints. This table shows the constraint number for different normalization methods, giving a mini-batch input or give a dataset with mini-batch optimization algorithms. From this table, it can be seen that the constraints get stronger for batch normalization with reduced batch size, while constraints get stronger for group normalization with increased group number. In summary, this part will illustrate that Huang can affect the model's representation, optimization, and generalization. We attribute that its scale invariant can stabilize training, its improved conditioning can accelerate convergence, therefore both benefits optimization. We showed that introduced stochasticity of normalizing or long batch dimension can benefit generalization. We also showed that the imposed constraints on activation of normalization can affect the model's representation. Note that the analysis shown in this tutorial is more like an empirical analysis with high-level theoretical insights. It is still difficult to fully understand normalization techniques, and we believe that it would be interesting to build a unified framework to further investigate the effects of normalization in representation, optimization, and generalization by combining the analyses above. Okay, here we discuss some challenges and opportunities in theoretical understanding of normalization techniques. Despite the recent progress of deep learning in terms of representation, optimization, and generalization, the networks investigated theoretically are usually different from those used in practice. One clear example is that where normalization techniques are ubiquitously used in the current state-of-the-art architectures, the theoretical analyses for deep neural networks usually rule out them. In fact, the methods commonly used for normalized activations, for example BNOAN, often conflict with current theoretical analysis. For instance, in the representation of deep neural networks, one important strategy is to analyze the number of linear regions. Well, the expressivity of a deep neural network with rectifier nonlinearity can be quantified by the max number of linear regions it can separate its input space into. However, this generally does not hold if batch normalization or layer normalization are introduced, since they create nonlinearity, causing the theoretical assumptions to no longer be met. It is thus important to further investigate how batch normalization or layer normalization affects the model's representation capacity. As for optimization, most analyses require the input data to be independent, such that the stochastic or mini-batch gradient is an unbiased estimator of the true gradient of the dataset. However, batch normalization typically does not fit this data-independent assumption, and its optimization usually depends on the sampling strategy as well as the mini-batch size. There is thus a need to reformulate the current theoretical framework for optimization when batch normalization is presented. In contrast, normalizing weights methods do not harm the theoretical analysis of deep neural networks, and can even attribute to boosting the theoretical results. For example, the Lipschitz constant with respect to a linear layer can be controlled or bounded during training by normalizing the weight with approximate orthogonality. This is an important property for certificate defense against adversarial attacks, and for theoretically analyzed deep neural networks generalization. However, normalized weights is still not as effective as normalized activations when it comes to improve training performance, leaving room for further development. Okay. It is glad to that there are some workers successfully trained residual network without batch normalization recently, but with normalization. However, they are still needed to fine-tuning the scanner to ensure the equivalent variance among layers, and with more sophisticated optimization algorithms,